Welcome to the molecular weight and its distribution under the head of polymer reaction engineering. In the previous lecture, we started about the things related to the molecular weight, and we discussed about the importance of a molecular weight as per this particular slide, that all molecular weight plays a very vital role in deciding the mechanical and chemical thermal properties of the polymer. And moreover, its change or this molecular weight also affects the processability of the polymeric system. So, we go ahead with this particular molecular weight approach in this particular segment, and we discuss about the various kind of molecular weight, how it distributed among the different type of a system. We will discuss in the due course of time. Now, the synthesis of higher molecular weight polymer is always not necessary, but polymers with high specified and improvised molecular weight is required for the many application. Now, why I am saying the polymers, they do not possess any kind of fixed molecular weight. The reason is that let us go to the this particular whiteboard, and we will see that this P1 represents the monomer. So, when we start the polymeric system or polymerization process, so this is one repeating unit. Now, this P1 at the start, at the outset, it may get combined with this P1 to give you P2. Now, this is my reactor, polymerization reactor. Now, here, now if you see that initially the P1 etc., they were present, but when the reaction was started or the polymerization process initiated, in that case there may be formation of P2. That means the two repeating units are combined. Now, at the carry on this particular polymerization a little further, then the reaction mass may have P2 may get combined with this P1 to give you P3. Similarly, P2 may have an option to combine with P2 to give you P4, right, and obviously this option is always there. Now, you see that in the reaction mass you are having P2, P3, P4 apart from P1. Now, if you proceed further, see the complexity of this particular system. If you proceed further, then P2 may get combined with P3 to give you P5. Similarly, P2 may combine with P4, which is earlier developed, P6. Similarly, P3 may have a chance to combine with P4 to give you P7. Similarly, the P3 may have a chance to combine on its own, give you P6. Similarly, P4 may have an option to combine on its own, so give you P8. Now, if you see this profiling, apart from this these products available in the reaction mass, there are additional polymeric chains having 5 repeating units, having 6 repeating units, having 7 repeating units, and another one is having the 8 repeating units. So, as a whole, if we talk about after some time, then this polymer system may have this type of a polymeric chains. Now, if you proceed further, then you see that the complexity may be like this. P5 may combine to give you P6. Similarly, P5 may combine with P5 to give you P10. P5 may have an option to combine with P4 to give you P9. Similarly, P8 may have an option to combine with P7 to give you P15. So, by this way, the chains of the polymer may have an ability to enhance themselves with respect to the different type of monomeric units or repeating units. Now, if you see just after say stage 3 or 4, now you see that how much different polymeric chains are available in the reaction mass. Now, see every chain, like whether it is P2, P3, P4, P5, etc., it represents the different number of monomeric unit. Now, let us have an example of suppose one monomer unit is having the molecular mass of x. So, P2 will have the molecular mass of 2x, P3 will have the molecular mass of 3x, P5 may have the molecular mass of 5x and so on. So, this is the molecular weight. Now, at the outset, there are two options. Either you truncate the polymerization reaction at the desired level of viscosity as the desired level of the function, or you keep on polymerizing different segments for the longer period of time. So, if you keep on setting this particular polymerization process for a longer application, then there may be a chance that higher molecular weight chain may get processed. In that case, the molecular mass of that particular polymer would be on the higher side. It may create the problem of processability, as I discussed in the previous slide. Now, in that case, you are compelled to truncate this particular polymerization process or terminate that particular polymerization process at some juncture. So, when you truncate this particular polymerization process, there may be a chance that your polymer mass may consist of a different chains with the different chain lengths, maybe P2, maybe P3, P4, P5, P6, P7 up to Pn and so on. So, in that case, you may not have an opportunity to analyze that how many number of chains are there, how many repeating units are there, etc. And that is why there is a usually a range of molecular weight for every kind of a polymeric system. And this may be from say 10 to 10 lakhs, etc. So, it all depends on that how much the physical and the chemical property you require in this particular polymerization process. So, it is a very crucial thing, and that is why if you recall that I discussed that initially the polymeric systems they are having the three different steps: initiation, propagation and termination. Now, initiation, as I told you in previously, this is your initiation step. Now, subsequent processes, when you started this initiation process, the subsequent processes are termed as propagation. Now, when you achieve the desired property based on your requirement with respect to the thermal, chemical, mechanical or the processability aspect or viscosity aspect, then you try to truncate. You cannot carry out this particular polymerization process for infinite period, because I told you that it may create a bulky mass. So, in that case you prefer the termination. So, at the outset, when there is a termination process, in that case you need to calculate the molecular weight, because one time we are saying that molecular weight plays a very vital role for the deciding the properties. So, the determination of this molecular weight is extremely important to carry out the further processing of any kind of polymeric system. So, based on this particular approach, there are different type of molecular weight things are given, and they discuss about the different type of distribution pattern for the molecular weight. I told you that from P, if at any point of time your molecular mass may consist of P1 to say Pn. So, that is why there is a distribution pattern for these molecular weight. So, based on this particular thing, we already discussed that polymers usually they are the mixture of molecules of a different molecular weight, just because attributed to the different polymeric chains having the different number of monomers. So, therefore, the average molecular weight and the exact distribution of a different molecular weight is usually required to characterize the polymer rather than the specific molecular weight of those polymers. So, there are need, as I discussed, there is need to control on the average molecular weight because of the processability, because of the thermal, chemical and mechanical properties. So that's why we are always looking for the proper molecular weight distribution to carry out the desired physical properties in those polymers. So usually this concept of average molecular weight is biased towards the larger and smaller sized of a molecule. So various methods are used to determine the average molecular weight of polymers. Sometimes colligative properties, sometimes light scattering things, sometimes the viscosity measurements, etc. So based on your requirement, you may choose the different protocols for calculating the molecular weight distribution. But before we discuss the protocol for the determination of these molecular weight, let's have that how we can classify these molecular weight distribution. So there are different methods or different protocols are available for this molecular weight distribution. One is that number average molecular weight. Now, the number average molecular weight is usually defined as the total weight of polymer divided by the total number of molecules. Now, it is usually the experimental method which usually count the number of molecules in the polymer. So, in this method, the measurement of the colligate properties of the solution is measuring by Mn. Now, this particular approach is represented by this particular equation. Now, before we go into the detail of this number average molecular weight, let us give you a typical plot of mechanical strength versus molecular weight distribution. That is a usual plot because by this particular plot, you will be able to learn more and more specifically about the importance of this molecular weight distribution. So, let us say that this is the molecular weight and here this is the mechanical strength. Now, here this plot is having 3 different segments. Now, A is the minimum molecular weight of polymer, this may be say 1000 etc. Above A, usually the strength increases rapidly up to the point B. After this point, this increases a bit slowly and reach to the limiting value of C. Now, this shows the critical point correspond to the minimum molecular weight of a polymer to exhibit the sufficient strength. Now, this particular concept is important because there are certain limitations, and these limitations you cannot carry out, as I told you, cannot carry out the experimentation or polymerization process for a longer time. Because of the efficiency of a process, you require the optimum strength, optimum property versus desired molecular weight. So, the critical point approach is extremely important in this case. Right. No doubt you may have a higher molecular weight and sometimes a slight enhancement in the mechanical strength. But if you carry on up to from point B to point C, certain quantum of energy, economics, these factors may get involved in this process. So, sometimes you may not get the feasibility to carry out this particular process from B to C. So, that is why the important point to carry out to analyze is the critical point. Now, this critical point is always useful while deciding the feasibility of any kind of a polymerization process. Now, go back to the number average molecular weight. Now, we discussed this particular approach in this particular slide where we are discussing about the number average molecular weight. Now, here the equation where or sometimes it is referred as, now here Nx is the number of moles whose weight is usually the Mx. This is summation over the overall different size of a polymer molecules from say x to x stands for from 1 to infinity. So, in other words, if we carry out this particular approach with respect to the mole fraction, it is represented as bar mn, where this is the mole fraction of molecules. Right. So, this type of approach is again important. Now, the most common method for measuring the number average molecular weight are the vapor pressure osmometry. Usually measures the molecular weight below 10,000 to 15,000. And another approach is the membrane osmometry for above say to 20,000 to 30,000 and some below 50,000. So, generally it is determined with the help of experimental tools, and let us have a brief look about these vapor pressure osmometry and membrane osmometry. Vapor pressure osmometry, it works by taking advantage of the decrease in vapor pressure that occurs when solute are added to a pure solvent. It is a very common phenomenon of chemistry. Now, this technique is used for the polymer with the molecular weight. They may have up to 20,000, though accuracy is best below, as I told you in the previous slide, that below 10,000. The next approach for determination of this is the membrane osmometry. Now, this membrane osmometry is a technique for the determination of molecular masses of polymer by means of osmosis, membrane osmosis. Now, it carries out in a membrane osmometer. Usually, this membrane osmometer consists of a two chamber. One chamber contains the pure solvent and other one is solution, and there is a barrier in between that is attributed to the semi-permeable membrane. Now, the solution container contains the solution in which the solute is polymer with an unknown number average molecular weight. Now, sometimes you may need to form the solution with the different type of a solvent, like sometimes hexane, sometimes of a different hydrocarbon solvents being used for the different type of a dilution to carry out this membrane osmometric process. Now, by measurement of osmotic pressure across the semi-permeable membrane, this gives the information about this number average molecular weight. Now, another segment of determination of molecular weight distribution, that is called the weight average molecular weight. It is a very common practice for the determination of or representing the molecular weight distribution. Now, it is usually based on the light scattering by the polymer solution, and it is greater for large sized molecule and smaller for small sized molecule. So, this method is usually accurate for higher molecular weight polymers. Usually, we do not prefer to have any upper limit of light scattering method to measure the molecular weight, but for lower limit it is 5,000 to 10,000. Now, this weight average molecular weight referred as bar MW, this can be described as the product of weight fraction Fx of the molecule whose weight is mx. Now, the mathematically it is represented as now this Fx is the weight fraction of molecules whose weight is mx, or this bar MW is concentration, this C is the concentration of X component, and this is summation nx mn square upon summation nx mx. Now, here the Cx is the weight concentration of mx molecule, C is the total weight concentration of all polymer molecules. Now Cx can see that is equal to Nx mx, and C is so this is the mathematical representation of weight average molecular weight, how we can represent this weight average molecule with respect to the polymeric system. Another, the third approach is referred as the viscosity average molecular weight. Now, as we know, in the previous slide we discussed that viscosity plays a very vital role, and if you carry on the polymerization process, sometimes viscosity may increase up to such a level that you can't process that particular polymer. So, viscosity is a very useful thing for the measuring the molecular weight of polymer. So, for larger molecule, viscosity is usually large, and for a smaller molecule usually it is a bit small. Now, this solution viscosity usually measures the viscosity average molecular weight. Now, this solution average viscosity average molecular weight, mathematically it can be represented as bar mv. This is the weight of x component mx Nx mx on A. Now, here A is constant. Now, viscosity and weight average molecular weights are equal when A is equal to 1. So, viscosity and weight average molecular weight are equal. Now, sometimes we may encounter this type of a scenario where viscosity average molecular weight is less than the weight average molecular weight. So, this scenario happens when A is in between 0.5 to 0.9. Now, it is usually 20% of weight average molecular weight, and it varied with the polymer, solvent and temperature. So, you can say that the different controlling parameter for this viscosity average molecular weight is the polymer, solvent and temperature. So, these are the governing factor for this viscosity average molecular weight. Now, another important part of this particular concept is the polydispersity index. Now, this polydispersity index, it offers a very vital role when we discuss about the polymerization process and the distribution of molecular weight, etc. So, this is used as a measure of broadness of a molecular weight distribution, how large or how enhanced this one. Usually it is the ratio of weight average molecular weight to the number average molecular weight. Now, it can be written as polydispersity index Pi. This is now this ratio depend upon the breadth of the distribution curve. Now, sometimes this particular curve plays a very vital role. We will discuss this particular curve later on. Now, this is usually 1 for monodispersed polymer or greater than 1 for actual polymer. So, it depends on the class of polymer which are being questioned. Now, the characterization of the polymer with the number average molecular weight alone without considering the polydispersity index may sometimes give you a mislead information. The polymer properties, they are more dependent on a larger molecular size than the smaller one. because then they are switches towards the monomer side. So polydispersity index depends on the breadth of the distribution curve, a graph in between the weight fraction and the molecular weight. Now we can have a look about this particular graph which we are describing here. Now here this is the molecular weight, and this is the weight fraction. Now here this is the number average, and this is the viscosity average, and this one is the weight average. So this is the molecular weight distribution in polymer samples. Now this particular graph is important in this context, that sometimes because of the complexity of the nature, you may require all three type of a molecular weight distribution pattern. So for this particular plot or this particular curve is extremely important to have an analysis, because sometimes you may require to have a wetting of a data during the polymerization process, and this particular approach is extremely useful to carry out this analysis. Now when we discussed about this particular approach related to the molecular weight distribution, and I told you about the importance of this particular molecular weight concept approach and how sensitive this particular approach is. That is why we discussed the different type of molecular weight distribution pattern, like number average, weight average, and viscosity average. So you can sensitize the thing that based on the polymerization process, based on the desired property of the polymers, based on the processability aspect, the molecular weight distribution plays a very vital role. Because sometimes you may have a bulky chains, then you may face a problem of processability, you may require certain other things. Sometimes the molecular mass becomes so thick that it may not be possible to remove that particular molecular polymeric mass from the reactor. So that is why the molecular weight distribution is extremely important. Now how to carry out this molecular weight distribution effectively and how to control this molecular weight distribution, we will discuss this particular thing in the control methodologies of polymer synthesis in the next lecture. So in this particular lecture, we have discussed about the molecular weight distribution. We have discussed about the efficacy of this molecular weight distribution to the polymeric system. We analyzed that how we can determine this molecular weight, maybe number average, maybe weight average, maybe viscosity average mathematically, because there are several experimental tools available as on date through which you can determine these molecular weight. And in the last slide, we discussed that sometimes you may require all three molecular weight distribution for a particular polymeric system to carry out the feasibility of that particular polymerization process. So we have gained the knowledge about these molecular weight distribution in this particular lecture. In next slide, because we have discussed about the efficacy of this molecular weight distribution, we will discuss that how we can control these molecular weight distribution pattern, how we can control the polymeric synthesis. So we will discuss this particular approach in the next lecture. Thank you very much.